The broadcast is now starting. All attendees are in listen-only mode.
Well, hello, welcome everybody to Coffee with Caleffi. Glad to have you on board, and thanks everybody for joining us and also for supporting Caleffi. So we're going to do a little tag team today. Cody and I worked on this presentation together, so I'm going to do some slides and he's going to do some, and there might be a point when we're both kind of going back and forth. So I think this will be an interesting topic. It was certainly interesting for me putting it together. It's a new topic for me as far as more of a plumbing topic, and we've been doing mostly hydronic over the past couple years. So let's roll with it and see what you guys think and gals think. Today, what we're talking about kind of appears in a couple different issues as far as pressure and pressure adjusting and regulation and stuff like that. There isn't one specific issue on this topic, but it threads through a couple different issues there. So some of the slides that you'll see today come out of these different back issues of hydronics. We try and always incorporate some of that information in our presentations, but that's where you'll find it. So what we're going to talk about is pressure today, and I guess for the purpose of this webinar, I define pressure as the exertion of a force upon a fluid. So basically, we use pressure in the system to lift the water, the static pressure. I'll show you some graphs as we go along on this to get the pressure into the building up to the highest point in the building. And also when faucets or taps are flowing, we've got to have enough pressure to overcome the resistance and all the piping and fittings in that. So we'll talk a little bit about what the codes are suggesting or requiring for pressures, what to do if you don't have enough pressure, what to do if you have too much pressure. So we're going to jump around a little bit, but these are the topics that I picked right out of the Uniform Plumbing Code, the IAPMO code book. And this is the 2018 version, by the way. It did change a little bit from the previous version, the 2018, on some of the verbiage in these bullet points that you see down there and what they suggest for minimum pressure, maximum pressure, what to do with relief valves, and also there's a little bit of suggestion there on water hammer, what causes and what to do. So every one of those we're going to go into in a little bit more detail. So I'll just keep rolling here. So for a well system, so most homes are either going to be, most buildings I should say, are going to either be on a public water system where you just have the water main possibly out in the street and a lateral line into your home, and you regulate your pressure into your building there. Now some homes, like my own, I've got my own well system. Most homes out in the country, this is probably more common to have your own system. It might share, a couple homes might share on a well, but basically there's going to be a pump in the well or above the well. It's going to pump it out, and there'll be a little pressure tank that the pump pumps into, and that controls the pressure going into the building. And now the way this works on this tank is this, let's consider this a submersible pump down in this well casing here. And so when that pump kicks on, it's going to pump the water up into the tank, and it's going to store some water in this little, this is very similar to a expansion tank on a hydronic system where there's a bladder across this tank, and as the water goes in there, it pushes up against the precharge on the air there. So you'll see what happens on this gauge. When the pressure comes in, the gauge will change, and when you take water out, the pressure is going to drop to a predetermined pressure where the pump will kick on again. Now most of the time those are going to operate around a 20-degree differential, and it could be a pressure switch, this switch right here, that operates at 30 pounds kick on, 50 pounds kick off. You can adjust those. You can buy different ratings. I think the one I've got on my house is a 40 pound cut in, 60 pound cut out. So then there's the spec on a typical, I guess that's a Square D brand pressure switch that you'd see. And this one even has a little manual lever on the side of it. So that's what's going to regulate the pressure coming in. Now what you'll notice on a well system is if you're in the shower and you're taking a shower, you know that the pressure is going to change a little bit. So it's going to drop down until it gets to the point where the pump kicks on. So you'll see a little bit more pressure fluctuation in a well tank system than you would on a main water line, where you're going to have a regulator that pretty much keeps it at a pretty consistent pressure. It doesn't drop as much as you might see on a well tank. Now here's a drawing that we found. This is an excellent drawing that shows exactly what happens on a domestic water system and on a pressurized system. So we've got the 2-inch main coming in. You can see cold water going over these water heaters here. And this is what I like about this. It shows all the appropriate components that you would have in a mechanical room on a system. You'd have your mixing valve for your temperature mixing. You'll have your expansion tank. You've got your recirculation pump. You'll see some temperature gauges, some isolation valves. In fact, what I'll do here is I'll toggle on exactly the components that we're going to talk about today, and you can see where they fit in a piping system, where the correct placement would be as far as, downstream of the check valve on the expansion tank, so it can handle an expansion of the tanks. T&P valve typically here for both temperature and protection for this vessel here. vacuum breakers, so you can't pull a negative pressure on these tanks and implode them or collapse them if you drain them down. So we'll go through here, and like I say, Cody and I will kind of split this up, talking about the different components. And certainly type in any questions. We've got a couple people monitoring questions as you type them in, so we can answer those as we go along. Hopefully we'll get to all the pre-submitted questions within the presentation. If not, Cody and I will certainly answer all those via email to make sure that we don't leave anybody out on the questions. So here's what we know about pressure. It takes just under a half a pound of pressure, 0.433 psi, to lift water up a foot. So if I only have to lift water up a foot in my building to get up to that elevation, I would need 0.433. Lots of times people will round that off to 0.5, so you can do the math in your head a little bit quicker, a little bit easier, but that's the exact number if you're doing a design that you want to use. So with that in mind, if we had to go up 10 feet, obviously we'd need 4.3 pounds of pressure to go up there. So as we have a multi-story building, especially a high-rise building, we need to adjust the pressure so that the bottom floor going up has the right amount of pressure, and we don't run out of pressure before we get up to the upper floor. So in this example here, we're looking at a 5-story building, and let's call them a 12 feet per story. And what that does makes the math come out pretty easy, that you have about a 5-pound pressure drop as you go up that building. So if you start at the pressure here, every story that I go up, the 12 feet that I go up times the 0.403 gives you that 5 pounds of pressure drop as we go up there. We got some better graphs coming up, but that's the number to know, is that 0.433 is the number that's going to push that water up through the building. So I don't know if you noticed on the code, I'm going to show you that code again, but we want to have at least a 35-pound pressure if we're going to have like flush valves in a commercial building to make the valves work. The codes are a little vague on what's accepted pressure. It varies from different codes to codes. If you're on the ICC or the UPC, or there might be some requirements from a local jurisdiction that can have a different requirement on that, or if you have fire sprinklers or something like that, it's going to change. But in this example, we wanted to make sure that we had a 35-pound minimum at every one of these levels here, so that's where the numbers come for this example. 80 psi seems to be the maximum I found in both codes, the UPC and the ICC. That has a lot to do with the fixtures that we use. Shut-off valves, ball cocks, and toilets have a pressure rating on them from the manufacturer, and you don't want to exceed that, or you could have problems with them leaking through, or have problems where the ball cock, for example, can't shut off tightly against a higher pressure than that. So that would be the maximum pressure that we'd want to see on a building. Now, I say that there's some exceptions to that, and it would depend on the risers in the building. You'll see a drawing of that come up here in a second, where we're going up through the building and then we're branching off at different floors. But so there's the numbers in my 5-story building. If I start at 55 pounds pressure, I drop 5 pounds at every floor. So I still have adequate pressure on the top floor of 35 psi. Again, counting that 12 feet per level or per story of that building. All right, here's a little bit more verbiage on the codes. Again, this is a uniform plumbing code, the IAPMA code. They consider inadequate water pressure below 15 pounds. Now, again, if you've got flushometers in the building, that's not going to be adequate pressure for to make sure that those seal and shut off tightly. It's probably bad on that, a urinal or toilet where you flush and it just keeps running and running and running. Sometimes that's an indication that the pressure's dropped too low, where it's not pushing that that's a diaphragm and shut-off mechanism up. So, and I would say 15 pounds, even in a residential building, would be not much of a shower flow for taking a shower, but that's the number that's out there. So excessive water pressure, again, anything over 80 psi, we want to make sure that we regulate that down. ICC, a little bit more verbiage in there. They say 80 psi, but they say with the exception of the risers, which I'll show you here in the next slide. You know, how in a multi-story or high-rise building, obviously, we've got to have enough pressure to get up to the uppermost reach, and so those risers could be operating at higher than 80 psi. Then we'll talk a little bit about expansion tanks and temperature and pressure TMP valves, how the expansion tank protects those and what the TMP valve does. Important if you're going to have any valve that can shut off tightly on a building where the expansion from the tank can't push back into the line, that we have some type of a vessel in there to accommodate that increase in pressure. And then water hammer, we're probably all experienced this in the building over the course of time here, is when you shut off a valve quickly against a flow, you can get that pounding noise that you hear. If the pipes aren't supported properly in the building, you'll hear that banging in the pipes also. No, we talk about both low pressure and high pressure. So if you don't have adequate pressure, one of the ways that we can boost pressure are these booster packs. And again, this is an engineer drawing here where we've got water coming into the system here, call that the suction side of the pump, a flow switch, make sure that we've got water coming into these pumps. And then these pumps will just boost up the pressure. If a low pressure coming in the line, again, you can adjust these pumps to whatever pressure that you want to have on the discharge side. Nice thing about these pumps now that we've got frequency drives and variable speed motors, we can actually modulate the speed of these pumps based on what the demand of the building is. So that makes it a little bit tighter control, a little bit of energy savings on those motors also. But oftentimes you'll see two of them like this. Sometimes that's for redundancy. If one goes bad, it's on a building where you make sure you always have adequate pressure. You might have one valved off and the other one can come online quickly when one fails, or if you have to service one or the other. And there's different types of pumps. You'll see some of the examples coming up next. And so this is the criteria. When you have to size one of these, you'll probably go to the pump manufacturer and say, okay, this is what my building requires. This is my design, kind of like the previous slide. I showed you the design there. And they're going to supply or ask you for this amount of information here. Okay, what's your suction pressure coming in? You know, what are you looking to have? What size flow rate do you need? All that's going to have to be crunched into a program or into the, you know, the sizing of the pump to make sure that you've got the right size pump for the job. And I thought these are pretty good examples of typical pumps that you see out there. This almost looks like a small shallow well pump. Basically, that's what it is, but it could be used as a booster pump. And so when they build these, they can change this, the number of stages that they put in here to change the capacity of that pump, change the motor, change the size of the connection. So these are really, when you get into these larger sizes, really are custom built to the application. You can see some vertical versions of it here. Some of these you can see have a kind of a brain on them, have the drive built into them, probably a variable frequency drive or some kind of electronic drive on that pump to vary the speed of it. These, of course, all be stainless steel. Since they're moving potable water, we don't want to have any rust or anything going that you would have with a you know, cast iron body pump. Now, examples of where you'd want to put a booster pump, maybe you've got adequate pressure in the house for the fixtures and stuff like that, but you might have a fire protection system that if that went off, you got to make sure you've got adequate flow for the heads that are triggered off, or another high demand load like, oh, I don't know, maybe a lawn sprinkler system outside that when all the heads are coming on, you got to make sure that you've got enough flow and enough pressure to maintain all that. So these booster pumps you'll see used occasionally on jobs. And here's, I'm not sure exactly what's going on this left-hand side here, but this is a little booster pump. It looks like a residential application. Confusing for me is, thanks Grundfos for these pictures, by the way, is, you know, almost looks like this is in somebody's bathroom and this might be a shower over here. I'm not sure exactly where this came from, but you can see it's nicely insulated and stuff. And also, I'm not sure why there's a pressure reducing valve on this pump, but what I'm trying to show here, so there's a pressure sensor that would sense what's going on with that. You can see a little bit of a well tank or an expansion tank there. And this is a variable speed pump again, so it's going to modulate based on the requirement or the demand of that building. Here's another one. This is a fairly typical pump that I see on residential applications where they need a little boost in their pressure, a little Grundfos, pretty much a plug and play. You can see inlet and a suction and discharge line, and all the controls are built right in under the hood there. So you basically plug that in and away you go. So nice looking. So if you have to have it in an application where it's you know, exposed or something like that, it's a pretty clean looking pump. So what we'll do is I'm going to let Cody do the next couple slides, and then I'll come back and we'll probably banter back and forth throughout this. So here we go, Cody, take it away. And thanks, Cody, for helping out.
Yeah, no problem, Bob. Thanks for having me on board here, and appreciate everybody's time here today. So yeah, Bob talked about pressure and systems and what you need to get to the top of a building and things like that, and he talked about booster pumps and scenarios where you might not have enough pressure or you need that pressure for adequate flow for those high demand loads. But on the other end of the spectrum, let's talk about how too much pressure needs to be controlled as well. And so here at Caleffi, we offer actually a nice line of pressure reducing valves. And again, you know, these valves are designed to take higher pressure down to a working pressure for your fixtures, for your, you know, your lavatories, your toilets, your showers, and whatever you're working with. And as Bob mentioned, per most codes, you're looking at an 80 PSI maximum. And so if you are above that, you need to regulate that and get it down to where it needs to be. So our flagship pressure reducing valve, as you can see here on the screen, is our 535H. We have it available in 1/2 through 2 inch sizes, wide adjustment range. From there, you can see right there that we've got unions on both sides, which makes it a great valve if you ever need to service it or pull it out for whatever reason to clean it out or anything like that. The unions also allow us a wide range or wide variety of connection types. And so you've got sweat, you've got press, PEX connections, NPT. Speaking of PEX, we've got PEX crimp and expansion as well. There's a lot of good things there. Another great thing about our valves is that we've got great fall off pressure numbers. And so the thing to remember with these pressure reducing valves is that you're setting them to a particular pressure, say it's 45 PSI or whatever, and that's going to be at a static condition. And whenever you do start to get demand, that pressure is going to drop off a little bit because you're not going to be able to maintain that exact 45 PSI. And that's what's referred to as fall off pressure. And so as you start getting more and more demand, the fall off pressure increases and goes from there. But like I said, we've got a great fall off numbers. It's all in our technical literature if you're curious about it. But it also can be locked with a screw on the top. We offer jumper nipples in case you're setting up a building and maybe you want to flush everything out before you get everything up and running. The option for the pressure gauge is right there as well. That's an NPT connection, so that way you can put a gauge in there. We offer it with and without. Really great valve. So, and
also,
next slide. Oh, go ahead, Bob.
That 180 degree operating temperature too, so it can be.
Oh yeah. I was going to go into that on another slide too, but
okay.
We're NSF 61 rated for the PRVs here, and we're rated for commercial hot, which is 180 degrees. And so if you are running into scenarios where you need to regulate pressure in a domestic hot water situation, we can do that too for you.
Thanks.
This here is just a nice little glamour shot that we found on some of the social media from Freiner Mechanical. From everything I've seen from those guys, they do a great job. It looks like here he's in the process of adjusting it. You can kind of notice, and I didn't point it out on the last slide, but we've got a big knob at the very top of that pressure reducing valve. And right below it, there's a setting window. And so what you can actually do is you can see what you're setting the valve to as you're making the adjustments. And so you can see there he's currently adjusting it. It's between on the knob or the setting window, it's between about 75 and 90. And if you got your really good glasses on, you can see the gauge is right about 80 PSI. So he's probably still adjusting that a little bit, but it's a great way to get it done, and it's a lot less cumbersome versus the couple of wrenches and trying to loosen up that jam nut and having a gauge somewhere down the line. But this is also a great slide to point out the fact that he's got adapters on there, going from our female NPT to press connections. And it's likely that this is probably just what the wholesaler had in stock, but just remember that we offer these in press connections as well. And thanks to Freiner Mechanical for this great picture.
And what I'd add to that, Cody, is you can actually turn this with your fingers. It's not like some of the other brands out there where you, like you say, you got to loosen the lock nut and have a crescent wrench to even adjust the thing. There's no way you can turn those against that spring tension, but that's the beauty of the Caleffi is at any point you can just grab that with your two fingers really and make an adjustment.
Yep. That's a great point, Bob. Yeah, it's really easy to adjust, we do offer that locking mechanism in the cap too. So if you want to get it adjusted and dialed in and you want to lock it down, so that way you're preventing a homeowner or a building maintenance guy from tinkering with it, you can do that as well.
Yep.
But we talked about booster pumps because you don't have enough pressure. We talked about pressure reducing valves because you got too much pressure, and now we're talking about applications here where you've got both. Okay, you've got this high-rise building, say for example here 30 floors, and you need to make sure you have adequate pressure at the very tippy top of that building, so that way they can use their sinks and flush their toilets as well. But the problem is you look here and you've got a booster pump there bumping up to 180 PSI, and this is a great example too where I think Bob talked about it earlier about how 80 PSI is the maximum, with the exception of the risers. Because obviously that riser, you're going to have to get that, all the way up to the top of that building. And so your riser is going to be anywhere. I mean, I've seen drawings where it's going to be upwards of over 300 PSI. But you can see here, what we've got is the building is kind of sectioned off into zones, typically 5 or 6 floors, maybe a little bit more depending on the height of the building or the height of the floors, but they're sectioned off into zones. And what you've got there is say, for example, floors 1 through 5 are one zone, and you can see there how the bottom floor 1 is 80 psi, whereas floor 5 is 60. And you kind of work up from there in those 5 floor zone kind of scenarios. And so you look at that, and like I said, you figure out how much that pump needs to produce, then you section things off and kind of go from there. So again, typically every 5 floors, but you know, PRVs to knock it back down on those lower floors. So that way you're not dealing with any issues with your fixtures. Now, Bob talked about, you know, maximum flow. You know, there's some manufacturers that only test so high. Higher pressure too can be a big issue. For example, when you're in the shower, if you are using some of those low flow fixtures and those water saving shower heads, you know, north to 80 psi is going to feel like you're getting an acupuncture treatment, and it might be a little uncomfortable for you. So you know, it's one of those things where not only to save your piping from, you know, erosion, corrosion, and make sure all your fixtures work, but make sure that you're comfortable in the shower as well.
Great.
Go ahead with the next slide there, Bob. And then, you know, same idea here too. I mean, if you've got a source of water from the top of the building, you can see here like the water towers and the New York skyline there. It's going to be the same idea. So you're going to have that pressure at the top of the building, and because of gravity, you know, that pressure is going to just increase as the goes down the building. And so again, at the bottom, you're looking at 180 psi. So you got to adjust for that. So again, 5, 6 floor zones, and knock it down to where it's necessary, and get yourself going there. So
got it.
Yeah. And then too, you know, I talked about earlier about how our pressure reducing valves are capable of being used in domestic hot water applications. So if you are using a single source water heater or a single source for domestic hot water in a building, you know, you're going to have to be able to control that as well. So again, make sure your PRVs are rated for that, as ours are, and they're rated up to 180 degrees, which is commercial hot for NSF 61. Another great thing to mention on here, we you know, Bob talked about recirculation pumps a little bit in the beginning. I would really caution people in applications like this. You don't want to recirc across a PRV, and there's ways around that. You know, you could have a domestic hot water source per pressure zone, you know. There's other ways of doing it as well. And I think this is actually a good time to mention that in September of this year, our colleague Kevin in North America here and our other colleague Claudio out of Italy are going to be doing a great webinar on domestic hot water recirc in high-rise buildings. And so if you're curious more about domestic hot water recirc in these taller buildings, that's going to be a great webinar to check out. So
yeah, thanks.
Yep. Go ahead to the next one there. This here is actually our cost fighter pressure reducing valve, and you can see here it's a little bit more compact, thus we call it the PresCal compact. And you'll notice how there's only a union on one side. We've got female NPT on the outlet side of the valve. This valve is only available in 1/2 and 3/4 inch sizes. So these are going to be your typical residential applications, or, you know, maybe it's a condo complex or something like that. You know, you're losing a lot, or I shouldn't say a lot, you're losing a few of those really nice features from the 535H series. You don't have the big adjustment knob on the top with the setting window, but you still have a great cartridge assembly that is made very similarly to the 535H, the nice, little bit nicer model, or higher on the food chain kind of model. You got the option with or without that pressure gauge as well. And then that union on the inlet side can be, you know, same thing, sweat, press, NPT, PEX, whatever you decide. This is a great valve. I think the next slide here, but I don't know if you have anything to add, Bob, on this slide.
No, I think you nailed it there. That's you're doing great.
All righty. Well, perfect. This next slide here is just some nice little advertising, trade advertising spots that we've done over the years. We're touting that 533H, that PresCal compact on the right there, as being the world's most recognized pressure reducing valve. And this valve is quite often counterfeit especially in the Asian markets. And so if you see anything similar to it with that kind of, it's considered an inclined pressure reducing valve where it's kind of leaning back a little bit there, you'll notice that there's a lot of similar designs, and some of them even have our logo on them. You're not going to see them here, but typically, like I said, in the Asian markets where there's a little bit less restriction on that kind of fun stuff. But another great thing to point out in these advertisements is the QR codes that are right in there. Bob's circling one there on the screen. QR codes are something that we are actually starting to introduce on a lot of our product. And what you'll find when you order our product is it'll have a bright yellow sticker on it with that QR code. And with that QR code, you can scan it with your cell phone, and it actually comes up with a playlist on YouTube, and that playlist is going to be all the corresponding videos relating to that particular product, and usually the first one is going to be what's referred to as our installation tips video. And so you're going to get somebody there that's teaching you best practices with the valve or whatever product the QR code is relating to, and things to make your life easier. So in case those instruction manuals grew legs and ran away or anything like that, but maybe you still got the box, you can scan that QR code and get yourself going.
Yep.
Alrighty, so this guy right here, we talked about making sure that you're controlling the pressure when the pressure's too high in your building. And so when you're sizing up a PRV or a pressure reducing valve, everybody thinks about sizing that around the maximum flow. It's very similar to mixing valves as well. Everybody sizes it based on the pipe size. And what you got to remember is that these have PRVs, and it doesn't matter if it's ours or anybody else's, PRVs have a range of control. And you look there, Bob's kind of circling there, our 1.25" model, 535H, has a design control range from 5.3 to 34 gallons a minute. And so when you are designing these systems and you're putting these in place, if you are putting that big 2-inch PRV on a system, maybe it's a residential system, you got to remember that there's going to be scenarios where maybe only one faucet's going to turn on, and you really got to account for that. And so what we've got here actually is PRVs that are piped in parallel, and we consider these kind of high-low assemblies. And the idea here is that the smaller pressure reducing valve is going to handle those low flows scenarios so as not to stress the larger pressure reducing valve. And so what you notice here is that the smaller one is set to 70 psi and the larger one is set to 60. Even with our pressure reducing valves, you can do that high, medium, low kind of scenario if you do need to control across a broad range of flows, which is pretty typical in a lot of buildings. So just make sure, again, that you're sizing based on maximum flow, but you always got to consider the minimum flow requirements as well.
Well put.
Yeah. And then when you talk about pressure in buildings, you can talk about scenarios, like I said before, where you're going to have 300 psi, and there's typical ratios for inlet to outlet pressure on these pressure reducing valves, and what Bob's underlining there is your ideal ratio there is going to be 2 to 1. And the idea there is say, for example, you got 100 psi coming into the building, you got to knock that down. You don't want to knock it down any lower than 50 psi. So that would be a 2 to 1 ratio. Okay. But say, for example, you've got 200 psi, like the drawing down here below, and you start taking that thing from 200 down to 45. That valve's not going to be happy, and that valve's going to let you know about it. And so it's going to make a lot of noise. It's also going to wear the valve and the cartridge down quite a bit. You're going to run into a lot of wire draw erosion and things like that inside the valve. And so if you've got scenarios where you've got high pressure in a building like this, especially on the lower floors of a high-rise building, don't be afraid to put these in series. Again, so you're stepping it down in increments. So like in the drawing down there, you're stepping from 200 psi down to 100, and then that second PRV is taking it down to 45 psi. I do believe this is my last slide. When you look at pressure reducing valves, you want to make sure that you're maintaining them. Typically, especially in these larger commercial buildings, you want to get these on the maintenance schedule. You got a nice picture here of one of our pressure reducing valves that's got some pretty good gunk in there. And so one thing to kind of make note of is that we have a screen that encompasses 360 degrees right around the cartridge, which is going to be really good because you've got more square area to kind of collect stuff on.
Yeah, so basically here, we got a lot of screen to protect the valve. This is where your problem's going to occur. If you get dirt in here, the valve's going to seep through and it's going to overshoot the pressure that you set it at. So in this example, they had it set at, let's say, 45 pounds, and they come back at an hour later and the valve's up to 80, 90, whatever the incoming pressure, and it's because of the debris between this seal right here that causes it to go through there. Now the screen's going to get as much as you can. Obviously, you can't make this too fine a mesh. It would plug up instantly. So there's kind of a balancing act there on what mesh we use to give adequate protection and still not plug up with just solder flux or something that's could completely plug up the screen. So I think we got a pretty good balance on the size of our screen for the the job that we're trying to do. And you can see down here where some of the debris is sitting in the bottom of the body there too. So that's what I'll usually indicate. It's the indication of this is the pressure keeps increasing over what you've set the valve at. And that's a nice thing about the Caleffi with the gauge on it. That's exactly what that gauge can be used for, is troubleshooting. If you come in there and you set it at one pressure and you look at it 15 minutes later or the next day or something like that, and it's beyond the pressure that you set it at, which you can still see in your window, by the way, on the valve, that indicates that you probably want to take that apart and check and see if you got some debris, Teflon tape, dirt. I can see on this application here, anything can get in there and cause that problem. So the beauty of this valve also is, right there is how you take this cartridge out, and you can almost do it by hand. It takes a channel locks typically because you got an O-ring seal up here, but you don't have to take like 18 bolts out of the top of this regulator to get it apart and service it to clean it out, or if you have to change a cartridge because something got damaged in here from a sharp rock or something, you just unscrew it right here from the body and this whole cartridge can be just replaced. So it's a really very simple valve to clean or to maintain or to take apart and check if you've got something going on in there that shouldn't be going on in there. All right, to make a long story long, we'll talk a little bit about thermal expansion tanks next. How are we looking for time? Yeah, I think we're okay. So if you have a water heater, and I'm assuming you do, or you should have one, they're kind of nice to have. What's going to happen is when you put water in this vessel and you heat it up, it's going to expand. Now, most of the time, this water could just expand and push its way back into the water main, and you don't notice an increase in pressure on a gauge or in the tank here. What's happening more and more often is we're seeing backflow preventers on buildings, either out in the water meter pit or somewhere inside the building. The local jurisdiction might require that for protection on their water mains. So if you have a check valve, if you have a solenoid valve, if you have any normally closed valve here, what happens when this water heater heats up, this is what you're going to see right here in this little graphic over here. We start at 70 degrees. As that burner comes on and the temperature starts going up, the pressure is going to start going up. And if there's no place for that pressure to be accommodated, you can see what happens here. We're blowing the lid off. Now you could, in fact, cause a tank to rupture, split a seam, or a split or weld or something like that. So we've got to be able to handle this increase in pressure as the tank goes up. One of the things that will do that for you, which isn't really what it's designed to do, but the pressure relief valve here. Now, typically on a residential water heater, this valve is going to be 150 PSI and 210 degree where it starts to relieve. What'll happen is if you get up at that 150 PSI, they'll start to drip or seep a little bit like that. And if that pressure keeps going up, eventually this valve is going to open up. There's just basically a spring in here. That valve is going to open up and it's going to discharge a big stream of water, and it's going to make a mess somewhere unless you have that piped into a drain. So the valve will seep at first. If you see a valve that's dripping on your water heater, you see a puddle near your water heater, you probably got this condition going on where somebody's maybe added a backflow preventer or put a check valve somewhere out on the street that you don't know about. Your pressure's going up, your valve's trying to protect this vessel. That's not really what we want this valve to do. This is really a safety valve. We don't want this to be a maintaining valve to take that pressure. And by the way, you're wasting water when you do this also. So a better way to do that is put a thermal expansion tank in there. And what I found is when I started searching through the codes, more and more the codes are requiring this. Even if you don't have a check valve, you know you don't have a backflow preventer, you know you don't have a solenoid or some valve that's normally closed, they're asking you to just include a thermal expansion tank on a water heater. And there's a special tank made specifically for domestic water expansion, because obviously you don't want the tank rusting. And here's an example one, and thanks to Amtrol for permission to use this, by the way. This is called a Thermtrol instead of an Xtrol in the Amtrol brand. The Hydronic one's an Xtrol. In the domestic water version, it'd be called a Thermtrol. And what's different about this tank, a couple things. Usually it's a 3/4 connection instead of a 1/2-inch connection up here. And you can see there's a lining inside here. So the lining, if this is a steel tank, obviously we don't want the steel touching your potable water here. So they'll put this lining in there that keeps the tank from rusting and from getting rusty water. But they also put something in there for bacteria protection. So it's got a little bit of a liner with some kind of a chemical or something built in it so you don't get bacteria or anything growing in there. The other thing that they're starting to do is put little turbulators in here. So if water goes in here and water doesn't come out, that water could get stagnant over time. So when water flows across this tank, it kind of induces a little bit of flow in here. So we're kind of, I guess, changing or switching that water from time to time. So don't try and use just a regular hydronic expansion tank. You'll get rust, number one. You won't have this protection in here. And also you want to have the device in there, the little turbulator, the little orifice in there that's inducing a little bit of flow through here. Like an expansion tank on a hydronic system, you have to check and adjust the pre-charge. Most of these will come out of the box at 45 PSI, and the reason for 45 is because that's what most regulators are factory preset. I know ours is, and our competitors all set their pressure reducing at 45 PSI, so the tank is pre-charged to that same pressure. Now, if you are going to change the pressure in your system, obviously you want to adjust this pressure accordingly too. So one thing I'll say, if you want to see what happens to a water heater tank that just keeps running, the burner keeps going, and there's no expansion or relief vessel on it, excellent video here from the Mythbusters where they exploded a tank from a long distance away. On a tank that ran away and didn't have any relief on it or any protection for the expansion, thermal expansion.
Hey, Bob, I think I'm back. Can you hear me?
Yeah, sound good now.
Oh, perfect. Well, I just wanted to point out, too, that, you talked about backflow prevention devices or check valves or a normally closed valve, but just another thing to think about, too, is that pressure reducing valves can cause a need for thermal expansion tanks as well, because in most cases those pressure reducing valves won't allow backflow depending on the inlet to outlet pressures and things like that.
Yeah, that's a good point. Some of the valves out there have a bypass that lets water go backwards, like Cody was saying. But if your pressure out there is higher, you can't push against pressure that's higher than what's coming in. So that's not an absolute protection. You really want to consider putting the expansion tank. And I think, like I said, some of the codes are requiring it now. So let me see if I got all the talking points in that. Yeah. So one thing that I noticed that happened where I was working years ago in Park City, Utah, is we started getting calls all of a sudden out of the blue that people's water heater valves are starting to drip everything out. Maybe there's a bad batch of relief valves out there. And what had been happening is the water department was going around and replacing the meter yokes out on the street. We had meter pits there, and they were putting in meter yokes with BFD's backflow preventers built into it to protect their potable water system. And they weren't telling the homeowners, or at least the homeowners weren't aware that they had to go and put an expansion tank on that to prevent that relief valve from popping. And these are just some glamour shots of what we've been talking about here as far as the expansion tank there. You can see usually the color's a little bit different on them too. If you're using the Amtrol brand, it's typically a gray tank in the Hydronic, and it's usually this beige colored tank on the Thermtrol and the domestic water tank. And like I say, the connection is usually a larger size on the domestic tank than it is on the thermal expansion tank for Hydronic. And there's an example of a pancake style expansion tank on the Hydronic side of this. Pretty nice setup here. Looks like they've got two different boilers, a gas-fired electric boiler backup for the low rates, probably up there on the power. So where were we? Yeah, again, some more, boy, it was shoehorned in there, wasn't it? Another example of a relief valve. What I would also caution you about on a relief valve, two other things actually, is you want to have this discharge tube put on it so that if this thing does go off someday, either on purpose or by mistake, that it discharges down the floor, that it doesn't blow out on the wall. In fact, that should go down to a drain or discharge somewhere safe. I guess I would say that it's not going to cause damage inside the building, inside the home, especially in a closet like this with all this nice woodwork around it. And the other thing on this valve, when you go to replace a valve like this, you got to know the size. On this little tag, it's going to tell you the pressure rating of that valve, typically 150 on a domestic tank. It's going to have the temperature, 210 degrees, just under boiling. And also it's going to have a BTU rating on it. So you need to know what the BTU rating on if it's a gas fired on the burner there, or the, do the conversion on the electric elements here, and make sure that that valve is sized for whatever the burner can produce for the discharge of that valve. Now, most of the residential ones start pretty big, I think at 690,000, so rare to find a domestic tank with a higher BTU capacity than that, but more importantly, on commercial buildings where you might have a big burner, high output water heater like we showed on that very first slide, you got to make sure that you're putting the right relief valve on there for the application. And over here on the right, again, the expansion tank. I don't want to get into the right side up, upside down issue. That's a controversial thing, it seems, on all the chat rooms these days about proper orientation of the tank, but we'll talk about that maybe on some future date with the tank manufacturers. And you can see one of our mixing valves here. So they're operating this tank at a higher temperature. They've got a mixing valve to mix it down to a safe temperature. Vacuum breaker here. We'll talk about that in an upcoming slide here. This is a really nice installation. You've got some unit strut in there, support and all that, really professionally done. So thanks to Greenpoint for that nice work and sharing it also. All right, a little bit more about the temperature and pressure relief valve. I think I talked about that, but again, it's called a TMP valve because it does two functions, temperature and pressure. These need to be checked from time to time. I've seen them where they lime up and they won't, if you go to pull the lever on them and they won't discharge, it's kind of limed shut. I think theoretically the manufacturer wants you to test these yearly, pull the lever on it, make sure that they discharge. What you're going to find if you do test them, sometimes you'll pull the lever, yeah, they discharge, but then they don't shut off and you're replacing it. So just plan on having one with you if you're going to start pulling relief valves and checking them for discharge. There's a good chance it might not shut off and you're going to replace it anyways. And then the other thing, usually when they go off on high temperature, they won't reseat. There's a thermal element that comes off the back of this that goes in there and senses the temperature. That needs to be in the top portion of the tank. You can't have the thermal relief valve up here. It needs to be into the vessel, which becomes a challenge, as you'll see here in the next slide, when you have a tankless water heater where you put the relief valve. So there's the TMP valve on the domestic tank there. Another example here. Now this is a little bit, I don't want to confuse you here, but these are what's called a reverse indirect tank. So the tank capacity is actually the boiler water, and then inside here there's a bunch of copper coils. So these tanks, you're going to see two relief valves on it. You'll see one relief valve that protects the pressure in the tank, typically the 30-pound relief valve like you would have on the boilers. And then up here you can see where they've cut one in on the top. That's the TMP valve that's protecting the temperature and pressure in the coils that are in the tank. So a little bit different application, but that's why you're seeing multiple valves on this tank here, because it's a reverse indirect tank. And there's the tank protection valve. Water hammer arrestor. Let's see, we got 10 minutes here. We're in good shape. All right, so this is what happens. Anytime you've got water flowing, this is called dynamic flow here. Now, water is moving. It's not static pressure that we would read with a gauge here. The water is actually flowing through a valve. And if you shut that valve off quickly, what happens is you get this hydraulic shock, it's called, sometimes called elastic shock, because when you stop water quickly, this is what happens, kind of crunches up like this. I guess that's a pretty good graphic of it. And when that happens, you can get a really high pressure surge. So this valve, let's say we were coming in here at, 80 pounds pressure, and you've got a quick acting valve. That could be a solenoid valve, that could be valve on a commercial dishwasher, that could be a lawn sprinkler valve, that could be a valve on a fire sprinkler, anything that could shut off quickly causes the shock wave. And look what happened to the pressure here. So it comes in at 80, we shut this valve off quickly, we got this hydraulic shock, and that thing spiked over 400 psi, 410 psi spike. Notice also that it does this here, and this is why I think they call it elastic shock, where it actually goes up and it actually drops down below that pressure that it was set at coming in here. Let's say the 80 pounds pressure. You can see we've got some low points on here, and it's going to do this a few times like that until it stabilizes back out, until this the shock has been absorbed through the piping in the building or through the whatever this is connected to on the other end, can absorb that eventually. But thanks to the folks up at Suchi for this good example of what happens when a valve closes quickly. And by the way, you can even do that manually shutting the ball valve. In fact, where you'll see this happen sometimes is when the firemen are running a fire hydrant out on the street, and they put the wrench on it and they crank it down quickly, and everybody on the street has a relief valve pop on their water heater because they just set up a big shock wave in that main, which then goes right into your house and can pop the relief valve on your water heater, on your fire sprinkler, something like that. So we want to be able to address this. We want to be able to maintain, the constant pressure. We don't want to see this spike when a valve shuts off close, because everybody has a valve like this. Your wash machine has a valve like this. Even an ice maker has a solenoid valve in it. And by the way, Sue Cheap does make water hammer resters all the way down to a 1/4-inch tube size that you put on the back of your refrigerator when you hook up your ice maker. So when that solenoid valve shuts off, that little mini arrestor on there handles that shock wave. And another place you're going to notice that, if you get a call from a customer and they say, I got a drip coming out of the backflow preventer that you put on my boiler here, or you go and they say there's a puddle on the floor under it, and you get there's no water coming out of it, looks fine now, what happened? Well, that same water spike, that pressure spike, can cause this valve to come off its seat, and you'll get a little bit of water. It'll just spit out for a second until that hydraulic shock wave dissipates. So if you happen to be there at the very instant that a valve shut off really quickly in that building, you might see this little cylinder, the little piston here, just shuffle real quick, and it's going to spit, and they'll do that time and time again, and eventually you lose the seal in here, and this thing just drips and leaks all the time. Most of the time, that's caused by the high pressure fluctuation. Now, a water hammer arrestor can handle that. I know what some of the other plumbers do is they'll put an additional check valve right here upstream of this. So if you do have that shock wave, that first check valve, the swing check valve, will just clatter once or twice, dissipate that shock wave before it hammers your backflow preventer. So if you go and you're replacing backflow preventers on a job over and over and over again, it's probably not the backflow preventer. You probably got a water shock condition going in there. And so here's probably a really good graphic that explains what happens when we quickly close this valve, and that shock wave now with this water hammer arrestor, it dissipates that. So think of this as just almost like a shock absorber on your vehicle. It's got a piston in here and it's got a seal in here. And so there's an air chamber, a little air space up here separated from the water here. And so it just pushes that up there. This will probably bounce up and down there until that shock wave is dissipated. Now, occasionally, a plumber will make their own and say, well, I'll just put a 12-inch piece of copper pipe and put a cap on it. And what will happen when this fills up for the first time, you'll captivate a little bit of air in the top of that little stub out that you put up there. Well, what happens over time is that you'll lose that little air bubble in there. That air will, get absorbed back into the water, and your air bubble slowly but surely goes away. And now this is just solid water, and it's not going to give you any protection from that water hammer because your air bubble's gone. So this is really the best way to do it. And obviously these come in a lot of different sizes depending on the application. So either contact your rep or the manufacturer and make sure that you size it properly. There's probably a classic example of that. Obviously a commercial dishwasher, I don't know if you can see it here, but a solenoid valve here, quick closing valve, and you can see 2 water hammer arrestors, and I'm not sure exactly why. Maybe they only had that one size at the wholesaler. This guy wants to make sure that he's positively got the water hammer sized properly to handle the this valve shutting off quickly. So yeah, you could stack them just like you do PRVs or anything else, or you could just get a larger single size, but that's what it would look like. And by the way, these water hammer arrestors really want to go as close as possible to where the water hammer is being generated, because I've had people say, well, can I just put a water hammer arrestor next to my backflow preventer? I said, well, it would do a better job if you put it out where that water hammer is being generated at the solenoid valve, which is what he's got going on here, really close to where that valve is going to shut off. So he's going to catch that hydraulic shock wave right here close to the thing. If I put this back at where the water came into the building, now I got that shock wave continuing down through all my piping, and I've seen piping actually blow apart from a shock wave like that when they shut off a main and the water main jumps right out of the street because they shut off a 300-pound main quickly and just bang that shock wave through the whole system. All right, makes sense? I think it's probably about the last one we've got here. We're looking pretty good on the timing. So I think I showed you a similar slide a little bit earlier. You can see there's a nicely piped system thanks to they do a lot of nice work. I see their work on Instagram all the time. It's just look how nice and clean and neat everything is. Even use the ProPress on the pressure relief valve tube here. But so pressure relief pipe down to the floor, maybe even down to a floor drain. There's a thermostatic mixing valve to protect the homeowner from high temperatures that they're running this tank at. And you can see here's the addition of a vacuum relief valve. Now, some codes require this additional valve, and again, that'll have to be a ASSE listed valve for the application, but it just allows air to come into here, so you can't, again, suck a negative pressure of vacuum on that tank and have it collapse inward, actually, is what it does. The other thing that can happen to a gas-fired type of water heater, if you don't have a valve like that and you get that negative condition, it can actually squeeze the flue pipe in the center closed. I thought I had a picture of that in here. So it's not just the tank itself will collapse, but you could actually collapse that flue pipe going up through the center of the tank, and now the burner kicks on, and you've got an issue with flue gases not going up through the pipe properly and possibly spilling in the room and having a CO issue. So that's where this device gets added in for that protection. I don't see them that often, to be honest with you, but I see pretty much every application that those folks there do that they put one on there. Maybe their local jurisdiction is requiring them, or the inspector that inspects that job. All right, so here what I wanted to show you, so let's say you've got a situation where you suspect you're getting a pressure spike. Well, how do you know that unless you can be there at the exact moment that it happens? So I threw in here a couple examples of gauges that you can put on that can record pressure over a period of time. This is a little data logger. Dixon, I used to have a chart when they had like this round piece of paper with a little pen that was on it, and it would record just like a seismic graph of the pressure going up. So you could put a recording device like this on it. In fact, probably this one's even Wi-Fi compatible that you could watch this remotely. I'm kind of old school. I've got this valve, this gauge right here that I built up. I call this a lazy hand gauge. So it's got the regular pressure gauge needle right here, the black hand, and then this red one, you turn it, you can see the little thumb screw on it, turn it down against that one. And what it's going to do is, let's say this goes up to 50 pounds of pressure and you get a pressure spike, obviously it's going to move the red needle, and the red needle is going to capture that high pressure spike. So if you go back the next day or a week later and say, gosh, it went up to 200 pounds, well, you got a water hammer, you got something going on. Or if it goes up there and stays there, it could be your pressure reducing valve is leaking through. So this is a good way to capture information when you can't be there to catch it in the act, so to speak. And there's, obviously a lot of different brands and types out there.
But yeah, like Bob was saying, it's a Pete's plug, and what you've got inside of that plug is basically a rubber gland inside of there. And so typically you're going to want to get that needle a little bit wet, or lubricate it in some fashion, and you can shove that guy in there. At that point, you can have a gauge. Typically, most of your needle type temperature probes as well will fit into the Pete's ports as well, and this will allow you to check pressure, temperature. You've got an example here in the middle of one of our balancing valves, and you can actually take differential pressure across that as well, so that way you can check to see how much is flowing through that particular valve. So, and again, thank you guys very much for your time. If there are any questions that we haven't answered during the webinar today, we'll make sure to get back to you in the future here, probably either today or early next week. And you guys have a happy Thursday and have a great day.